On August 19th, several math YouTubers posted their mega favorite number, or their favorite number greater than 1,000,000. And I decided I'm gonna join in on the trend right away. Okay, maybe not right away, but I'll make up for my delay with a number that blows everyone else's number right out of the park. My mega favorite number is infinity. See, it's the best number because it's the biggest number. There's no number bigger than infinity. Or is there? To understand whether infinity is the biggest number, we need to define a few terms. What is infinity? What is biggest? And what is a number? There are many kinds of numbers: positive, negative, rational, irrational, real, complex, but we're just going to talk about the cardinal numbers, which are the numbers that count things. The number 3 counts how many things are in this set, 7 counts how many things are in this set, and so on for every whole number. We call the size of a set its cardinality. Thus, every number can be defined as the cardinality of a specific set. By our definition of a number, we can compare the size of two numbers by comparing their corresponding sets. We can match elements from one set to another and see which set has elements left over. That one is bigger. If we match them up and there aren't any elements left over from either set, then the sets are the same size. Their cardinalities are equal. Earlier, we defined a number as the cardinality of a specific set, so infinity must be the cardinality of an infinite set. For our purposes, we'll use a very special infinite set, the set with every positive integer, 1, 2, 3, 4, 5, 6, and so on forever. Mathematicians call the size of this special set Aleph null. For now, we'll assume infinity means Aleph null. With these three definitions, number, bigger, and infinity, we can finally start to understand whether infinity is the biggest number. By our definitions, if infinity is the size of the set of positive integers, then the question really asks, is the set of positive integers the biggest set? So, is the set of positive integers the biggest set? It's clearly bigger than any finite set, because when we match up the elements, we'll still have infinitely many left over. But can't we get a bigger set by just adding a new element? Surprisingly, the answer is no. There's a key difference between finite sets and infinite sets. When comparing finite sets, you only need to compare them one way to figure out which set is bigger. If one set has elements left over, it's bigger. End of story. But not so for infinite sets. When comparing infinite sets, there's more than one way to match up the elements. For example, if we match up 1 with 1, 2 with 2, 3 with 3, and so on, then we have an element left over, 0. But if we match up 1 with 0, 2 with 1, 3 with 2, and so on, this goes on forever. You'll never run out of elements to match up. So if we match up the sets this way, there are no elements left over. I've just shown one way to match up the sets where an element is left over, and one way where no elements are left over. So is this set bigger, or are they the same size? When it comes to infinite sets, a set is only bigger than another set if there are elements left over every possible way you can match them. In other words, if even one way of matching them doesn't have elements left over, the sets are the same size. Thus, the set of integers from 0 onwards is the same size as the set of integers from 1 onwards. Instead of just adding a 0 to the set, what happens if we also add the negative integers? Now our set has every integer in existence, positive and negative. Is this set bigger than the set of positive integers? The answer is still no. We can still match up the sets so nothing is left over. Let me show you. It helps if we order the set of all integers like this: 0, 1, -1, 2, -2, 3, -3, and so on, alternating between positive and negative all the way out forever. Now with the set matched this way, it's easy to see how we can match it up with our set of positive integers. 0 matches with 1, 1 matches with 2, -1 matches 3, 2 matches 4, and so on, forever. Again, no elements are left over, so the sets are the same size. Even the set of all fractions, seemingly much bigger, can still be matched up with the whole numbers using a pattern like this. Is there any set bigger than the set of positive integers? In 1891, mathematician George Cantor found the answer to this question. He found a set bigger than the set of positive integers. A set so large that even with an infinitely long list, you still can't list all of the elements. What is this monstrous set? I'm talking about the set of numbers between 0 and 1. Let me show you. This is a proof by contradiction. Assume there is a way to match up the set of numbers from 0 to 1 with the set of positive integers. If so, we could list out all the numbers from 0 to 1 in an infinite list, like so. I will prove there must be some number between 0 and 1 not on the list. Take the first digit of the first number and change it to something else. Take the second digit of the second number and change it to something else. Continue moving down the list on a diagonal, changing each digit to something else. This resulting number can't be on the list. It can't be the first number because the first digit doesn't match. It can't be the second number because the second digit doesn't match. It can't be the third number because the third digit doesn't match. It can't be any number on the list. Thus, the list is incomplete. There's at least one number left over. Even if we add this number to the beginning of the list, we can do this same procedure again, so the list is still incomplete. Every possible list is incomplete, so every possible way of matching these sets leaves elements left over. Thus, the set of numbers from 0 to 1 has more elements than the set of positive integers. Cantor found a number bigger than infinity. In other words, he found another infinity. In fact, Cantor proves there are infinitely many infinities, each one bigger than the last. So it turns out my favorite number isn't a number at all. It's a whole class of numbers, and that entire class of numbers has extremely bizarre properties. Adding an element to a set doesn't make it bigger, unless you add infinitely many elements, and even then it has to be the right kind of infinity. Sets that have no end with extremely counterintuitive properties excites me. And that's why infinities are my favorite numbers.